Hello everyone and welcome to today's webinar. Today's webinar is titled Investigation of Stair Ascending and Descending Activities on the Lifespan of Hip Implants. My name is Christopher Iverson and I work here at Anybody Technology. And today I'll be the host of this webinar, and during the Q&A session in the end I'll be joined by my colleague Björn Engelund, who is one of our research and development engineers. In the Anybody webcast series, we host presenters who have worked with the Anybody modeling system to cover different use cases. And in today's webcast, we have a group of external speakers from Izmir Institute of Technology in Turkey. We have Associate Professor Sine Micin and her 3 PhD students, Ali Khan Alpkara, Mehmet Yilmaz, and Ahmet Sahin. And they will present their findings on the use of Anybody to estimate the boundary conditions to feed into a dynamic hip implant wear model. And this work is already published in a recent article in the Journal of Medical Engineering and Physics, so please go and check this out if you want the very details of the work. And the presentation will start in just 2 minutes. So just before we start, I'll give you a short general introduction and overview of the Anybody modeling system, if any of you are unfamiliar with the software or musculoskeletal modeling and simulations in general. But first of all, I would like to point your attention to the control panel, which appears on the right side of your screen. And you are very welcome to submit questions and comments via the questions panel during the presentation. We will try to address the questions at the very end of this webinar. And in case we do not get to answer all of your questions, we'll try to do so by email within a reasonable time. So let's begin by having a look at what the Anybody modeling system actually is. The Anybody modeling system is a software that allows you to do musculoskeletal modeling and simulations. And as input, it takes motion data as kinematics and forces, and it calculates the internal body loads as joint reaction forces, muscle activity, and metabolic energy. And at the moment, Anybody is used in a wide variety of areas and applications. And on this screen, there is a few examples of this as movement analysis, product optimization design, the field of sports optimization, orthopedics and rehabilitation, ergonomics with and without assistive devices, and of course in the automotive industry. And just to give you an idea of the typical workflow in Anybody, then it could look something like this. So you provide the recorded motion data as input, and then you can use the body models which you or others have built. You can then provide some kind of environment, which could be a special type of equipment, for example, an exoskeleton, as it is in this case. You can then use Anybody to combine these things and solve the muscle recruitment and run the inverse dynamic simulation. This basically means that we go from motion to calculate the internal body loads and the interaction with environment in some cases. You can then output the results and use it for some kind of post-processing, which could be, for example, with a finite element tool. But there's also many users who choose to close this loop completely by doing some kind of design optimization and then run this cycle multiple times. And this actually brings me to the end of the introduction, and I will hand over the presenter role. Thank you.
Dear all, thanks for coming to this webcast event. So I'm Associate Professor Dr. Şenay Micin, and we will be covering the latest publication, as previously mentioned. The name of the publication is Investigation of Stair Scanning and Descending Activities on the Lifespan of Hip Implants, and we are based in Izmir Institute of Technology. And this is the author's list of the paper, and we will be presenting it as a team together today. Yep. I'd like to mention where we are based in Turkey. We are based on the west coast of Turkey. So this city painted in red is Izmir, and maybe you have heard the name because of the earthquakes anyway. So we are one of the best universities in the Asian region because we were selected as the best research university in Asian region, and we are ranked as 4th in general in Turkey among the state universities. And very recently we got an award, leadership awards for higher education, which is known as the Oscars of Higher Education Awards Asia 2024. And last year we also were ranked as the best university for the satisfaction survey. So I would like to give some more information about my team. Next, please. Okay, so this is the ISTEC Biomechanics and Motion Capture Laboratory standard experiment performance day on an experiment day. So you can see our website address, biomechanic.lab@iyte.tr. So if you have any questions related to this webinar, you can directly contact me through this email address or just type from the website of the laboratory. So I was basically in the United Kingdom for 15 years, and recently I got back, so I received the funding. So I started this lab, and we have a Qualisys system in our laboratory. So we have 9 micros cameras and 1 tracking camera, and 14 reflective markers, 14 millimeter reflective markers are utilized for this experiments. And we have a Bartek force platform. We also have Dell's EMG sensor sets. In addition to this marker-based simulation MOCAP system, we have wearable motion capture system, Rococo, which is utilized mostly in film and art industry, but we also conducted some experiments to validate its use for gait assessment aims. And we have also our own homemade hip simulator. It has 3 degrees of freedom for rotation and 1 degree of freedom for translation. And this simulator is specialized on mimicking, simulating the activities of Turkish population, or let's say Eastern populations, because it can simulate some daily life activities specific to religious activities or yoga postures on different sitting postures, and in addition to daily life activities of like stair climbing, cycling, and sitting, that sort of things. So we have made also collaboration with China University, Xi'an, and we have 3D medical peak printer where we can do printing applications. And obviously we have anybody modeling system. We have 2 licenses and we run them on our 4 workstations. So this is my team. So I'm a graduate of Loughborough University. I completed my PhD in 2008. And based on this, I started my own research lab after receiving the funding from TÜBİTAK. This research is funded by TÜBİTAK 22-24 program. So Alican is about to graduate this month, so he's hopefully going to finish his PhD, and Mehmet and Ahmet Merşahin are still in progress, waiting for their studies to finish within 2 years' time. We were able to successfully produce journal publications from this research, so you can find this list on our website as well. And today we are covering this journal paper which was published in Engineering and Physics Journal. You can download this paper from sciencedirect.com easily, and impact factor is 2.2. It's a 3rd quartile journal, and people with backgrounds of medical engineering should be able to easily understand the content of this work. So today we will mention about this study where we have recruited 14 participants to perform walking, stair scanning, and descanning activities, in which we derived kinematic and kinetic data after we collected the data from Qualisys. So we used CAST, Calibrated Anatomical System Technique, full body marker set. And then we fed this data into Twente Lower Extremity Model in Anybody. So based on these boundary conditions for range of motion and force and moment data, we've fed them into the Ls-Dyna modeling software to calculate the wear rates of cobalt chromium on cross-linked polyethylene for these activities with a ratio of walk-to-stair ratio of 15.9 to 1 over 5 million cycles. So we calculated the wear rates. So details will be explained by my teammates. So I leave the word to Ahmet Merşahin for him to continue with the methodology part. Thank you very much.
Welcome, and thank you for joining us today. I'm Ahmet Merşahin, currently pursuing my PhD under the guidance of the Professor Mikcin. So today I will present 2 subsections of our methodology, the construction of the experiment, and data acquisition. In our laboratory, we rely on essential equipment for our research. This includes 9 micros reflective camera, software of the cameras, a Bartek force plate, and an AMG system. These tools enable us to conduct our study effectively. So our approach to preparing materials and system has been through ensuring that they meet the necessary standards for precision and reliability in our research. So we have set our reflective cameras and force plate to capture the data at a consistent rate of 100 frames per second, and we have used markers with 14 millimeter diameter. The dimension of our working volume and stairs have been designated as illustrated in the provided diagrams on slides. You can see them. So in order to proceed with the experiment, we have ensured that all participants met the condition listed here. Since this study aimed to analyze the healthy individuals, participants were observed and interviewed to ensure that they did not have any physical disability or any illness. And the minimum age for experiment was set as 18. And as for the body index, it was ensured that all participants don't pass the 30 BMI. Anthropometric measurements were taken based on the suggestion of the Anybody documents. So we have used full body cast marker set. This set consists of 2 types of setup. For static poses, 55 anatomic points, and for the dynamic poses, 47 anatomic points are designated as marker placement. So you can see the experimental flow I explained so far as a summary in the diagram here. Initially, participants receive a participant information form. After being briefed about the experiment, their qualification is assessed against the experiment criteria. If they meet the requirements, they proceed to sign the participant consent form. Simultaneously, the camera system prepared by performing calibration, and the measurements of the participant are taken by the physiotherapist. Once the participants are prepared, markers are placed on the subjects and initiating the image capture process. So here, every process you see are repeated for each participant until the number of subjects reaches sufficient number. So I'm going to end my part with explanation of activity cycle. Cycle of each activity investigated in this study is determined based on the literature research. The gait cycle is defined as the start with the heel strike of the of one foot and concluding with the subsequent heel strike of the same foot. This is also the same for the stair ascending. However, for stair descending, the cycle is defined as beginning from the moment of the toe and concluded with the subsequent toe of the same leg. So thank you for your participation. My colleague will continue.
Thank you, Ahmet. It is Mehmet Yılmaz. The multibody musculoskeletal model simulations are in my responsibility. Next slide, please. Alijan, thank you. The multibody simulations are performed in Anybody modeling system. The workflow of the process is as seen. We can divide this process 3 main steps: parameter identification, inverse kinematics, and inverse dynamics. Each step building upon the previous one. In this study, a marker-based full-body motion capture model used from the Anybody model repository. The model consisting of the upper extremity and Twente lower extremity model. We call it TLM2. The TLM2 model has 21 degrees of freedom with the 11 segments. Each hip joint is modeled as ball and socket joint, and each knee and ankle joints are represented as hip joint. The model contains 169 muscle model. Can you come before slide, please? Yeah. Parameter identification. In this sub-step, the model is linearly scaled in Anybody to develop subject-specific musculoskeletal model for each individual. Inverse kinematics. Then the joint angles are calculated through the inverse kinematic analysis by using the dynamic trials. Inverse dynamics, taking account the calculated joint angles and force plate data, the joint reaction forces and moments are calculated with inverse dynamics and muscle recruitment optimization algorithms. Next slide, please. As I mentioned previous slide, in this study we have used full body MoCap model from the Anybody model repository. Here is the measure configurable variables. Model we have used Twente Lower Extremity Model used. Scaling, there are several scaling methods in the Anybody model repository in the repository. In this case, we use XYZ scaling, taking mass and fat into account. Marker protocol. A marker set is developed according to CAS marker set to scale the model, minimizing the cumulative error between the virtual and experimental markers. Force plate type. Bartek force plate type for use. The marker and ground reaction force data are filtered to eliminate the noise. As a muscle recruitment optimization algorithm, third order polynomial muscle recruitment criterion used. Anthropometrics of subjects and position of segments used to set initial position and orientation of the segments. Next slide, please. With static trial, as I mentioned, generic model is scaled, which is shown in top left. As you see, gait activity top right. First, inverse kinematic simulation is performed. You can see it not use the muscles and ground reaction force, and then the inverse dynamics analysis is performed. Same procedure followed for the stair descending and ascending activities. Next slide, please. For to validate our calculations, the measured data from the literature used, which is the instrumented hip implant results from the Bergman at 2001 publication. The first row is our calculated results, and second row is from Bergman study. SCN table, in terms of the hip peak hip contact force, only 8% difference observed between our results and Bergman results. So the results are consistent with the measured forces. Next slide, please. The calculated joint reaction forces are divided by the mass of the subject to normalize values. As seen in the table, maximum joint reaction force are in the proximal distal direction. During the stair ascending and descending, the maximum joint reaction forces is approximately 1.2 times greater than walking activity. My colleague Alican now will demonstrate how this finding influenced the lifespan of the hip implants. Thank you, Alican.
Hello, dear guests. My name is Alican Tuncay. I'm a PhD student in Biomechanics Lab. Today, I will present the finite element methodology for wheel analysis under stair ascending, descending, and gait activities. First of all, I will mention about the literature data. The lifespan of hip implant under walking cycle in finite element method could be predicted as 25.7 years under the hip simulator conditions. In the literature, Evans et al. Studied at the lifespan of approximately 230,000 hip implants in 16 different countries. The average lifespan of hip implant lasts 20 years. The differences between the clinical retrieval and hip simulator or finite analysis method is more than the 5 years. So we can minimize the result between the clinical and hip simulator data. In this hypothesis of this work, the daily frequency of stair ascending and descending per day is calculated as 172 cycles, which is equivalent to 62 approximately 63,000 cycles for stair ascending and descending activity. While the patients with steps 3,040 steps per day, which is equivalent to 1 million per cycles. Which means that we assume that the frequency of walking is approximately 16 times higher than the frequency of stair ascending and descending activity. So we investigated the wear performance and longevity of the hip implants, adding stair ascending and descending wear rates on walking cycle according to walk-to-stair ratio, provide to converge our result with the literature data. Firstly, I will mention about the enhancing the model quality. There are 3 steps in this study. First of all, the pre-analysis steps, which is included the mesh type, order and section, boundary condition and loading condition, contact types, and material properties. We choose the brick element first order, and we choose the element form is -1, and we apply the constraint, loading, and motion activity. We choose the 2 different types, contact types. First one is the tight contact is no allows us to any rotation and the translation. While surface-to-surface contact is free to move and to translate in 3 directions. All materials in this study are selected as linearly elastic. We define the contact coefficient of friction and Archer wear factor. After we define the pre-analysis category in our prototypes in finite element, we need to check the sensitivity analysis, such as mesh sensitivity and scaling factor. Sensitivity analysis used to minimize the effect of mesh size or scaling factor numbers on the result of the finite element methods. After performing sensitivity analysis, we performed our prototypes in Ls-Dyna with shared parallel memory and double precision. After we performed our 3 different boundary conditions activities, we obtained the result of this study. These are wear rate, linear and volumetric, wear sliding distance, contact pressure, and contact area. After we obtain the result, we need to validate our result with the literature data. Hip simulator these data are obtained from the hip simulator, clinical retriever, and family site. After validate our result with the literature, we can report them. The figure 3 shows the loading and the rotation data for gait, stair ascending, stair descending activity. These are 2 graphics are illustrated in this graph. The first one is the versus time. The another one is rotation versus time. Figure 3D shows the applied loading and the boundary conditions. The shell of the component is fixed, so it is not allowed to any rotation and the translation. While the femoral head shown in the red, red one is free to move any direction. The loads is applied to the bottom of the side of the femoral head, while rotation is applied to the point at the heat center. We performed the 3 different boundary conditions, stair ascent, descending, and gait activity over the 5 million cycles. The linear inserted at the 45 degree on the flexion extension axis, which is mimic as the natural position of hip implants. I will mention about the mesh sensitivity analysis. Mesh sensitivity analysis is a vital process for each finite element, because in this sensitivity analysis we can minimize the effect of the mesh element size on the result of this study, such as contact pressure, wear sliding, linear wear, and volumetric wear graphic. Figure shows the peak contact pressure and wear sliding distance versus the duration. The mesh sensitivity analysis, we range from the 2 millimeter to 0.8 millimeter. And the variation in the output are less than 1%, the optimum mesh size is determined. In the literature, this study is only considered the one parameter, peak contact pressure or wear sliding distance or linear wear. In this study, we perform considering the two different parameters. Table 2 shows the effect of the element size on the contact pressure, sliding distance, and the wear depth. And we determine as an optimum mesh size of 1 millimeter. Another sensitivity analysis is scaling factor. Scaling factor means the required number of consecutive each steps, which means that in runtime of the one finite one model is approximately 8 hours. If we consider the 5 million cycles, the runtime of the all finite element is a huge number. So we have to determine the scaling factor. In this study, the range of the scaling factor is from 0.1 to 1 million cycles. The runtime of the model with the 0.25 million cycles is approximately 2.5 times higher than the model with 0.1 million cycles. And the optimum scaling factor is selected as 0.25 million cycles. After we perform the pre-analysis, perform the analysis and the sensitivity, perform sensitivity analysis, we can obtain the result. First of all, I mentioned about the contact pressure. The peak contact pressure values have obtained 6.32 megapascal for the gate, while the peak contact pressure is obtained 7.58 megapascal for stair descending and 8.33 megapascal for stair ascending activity. Figure 5 shows the cumulative linear wear depth of bearing linear and femoral head under 3 different activities. The peak cumulative linear wear depth is obtained as 0.195 millimeter for stair ascending activity. Figure 6a shows the total linear wear depth over the million cycles, and B shows the total volumetric wear of cross-linking bearing linear under stair descending, ascending, and the gate activity over the 5 million cycles. Well, we get back to the idea of this thesis. we consider the effect of different daily life activities such as stair ascending and the descending activity on the only walking activity. If we consider the only walking activity, the volumetric view rate is obtained as 80.8 millimeter cube per million cycles. If we consider all different effects on the gait cycles, the volumetric view rate is obtained as 22 millimeter cube million cycles. The percentage increase in mean volumetric view rates of cross-linking collinear linear and cobalt chromium head for the gait by adding stair ascending and descending activity compared to normal walking are predicted as approximately 7% for cross-linking linear and 12% for cobalt chromium head. We sum up this study. First of all, the volumetric view rates of cross-linking under walking increased by 16% by including the effect of stair ascending and descending activity. The linear view rates of cross-linking for the walking increased up to 3.27% by adding stair ascending and descending activities. The lifespan of EP implants under walking cycles could be predicted as 25.7 years in finite element and 20 years in clinical retrieval. We aim to minimize this lifespan of EP implant. In the current study, it could be predicted as 26.9 years for walking compared to 23 years with adding this stair ascending and descending activity. While estimating the lifespan of the EP implants, the researchers should consider the cumulative effect of each daily life activity rather than focusing on only gait activities for more accurate prediction of the lifespan of EP implants. Thank you for listening. If you have any questions, we will answer it.
Thank you very much for the presentation to all of you. Just before we go to the Q&A session, I would just like to say a few words about our online resources. I'll just share my screen again. There we go. So if you want to know more about Anybody technology, then you can go and check out our website, anybodytech.com, where you can find different events, special dates, and also previous webcasts. You can also check out our community website, anyscript.org. This is for people using Anybody. And here you can find multiple online resources such as our wiki page, several blog posts, and also links to our repository sites. It's also here our forum is located, so you can go and ask help from fellow Anybody users. Then we have a few upcoming events I would like to highlight. So on June 4th, we have a webinar about our new thoracic spine, ribcage, and abdominal model. And the registration for this is open already, so you can go and find it on our website and secure your seat. And if any of you happens to be attending either the European Society of Biomechanics Congress in Edinburgh or the Southern Orthopedic Association annual meeting in Miami, then please make sure to stop by our booth there and let's have a talk about musculoskeletal modeling and simulations. And to end the presentation, I would like to mention that we maintain a publication list of papers using the Anybody modeling system. And this list recently reached 1,000 publications. So this is really a great place to go if you want to get some inspiration on what have been done using Anybody already. And this brings us to the Q&A session. So Björn, you had time to look at the question. Could you read out the first one?